Hey, we have here today another integral. This one's from the MIT Integration Bee 2022. This was regular season problem number 1. We have the integral from 0 to 100 of the ceiling function square root of x dx. So first what I want to deal with is let's just go over the ceiling function real quick. I like to think of the ceiling function as kind of rounding up. So just for the ceiling of x, this will return the smallest integer greater than or equal to x. So a couple examples of that, let's say if we had 3.1, the ceiling of 3.1 will take us up to the next integer, say 4. But if we were getting the ceiling of just 3, we're already at an integer, so it's just going to return 3. Now for this integral in particular, we've got the square root inside of we have the square root inside the ceiling function. So what I want to do is look at the perfect squares from 0 to 100. So here we have all of our perfect square values from 0 to 100. And I think this is going to be useful with the ceiling function because we want to find these cutoff points so what we can do is actually break this up into a bunch of different integrals with bounds using this here. So for example, we could look at some different values, like we're looking at x from 0 to 100. So let's say when x is 64, if we put 64 in here, square root of 64 is 8, ceiling of 8 is going to be just 8. Let's look at a value between, like somewhere in here. So like let's say our x value is at 50. Well, the square root of 50 is going to be like, I don't know, let's just say it's 7.1. But keep in mind in our integral we have the ceiling of this. So the ceiling of 7.1 is actually going to be 8. What's going to happen with this ceiling function, it's going to simplify this quite a bit because when we break this up, each of our integrals is going to round up to an integer value. So I think let's look at the integral and see how this is going to work. To start with, I'm going to use this value and we'll just look at our integral from 0 to 1. Now at the 1 point, square root of 1 is 1 and the ceiling of 1 is 1. But for any of these other values from 0 to 1, like if we put a half in here, the ceiling is still going to round it up to 1. So this integral is just going to be really simple. It's going to be from 0 to 1 dx. Now next we'll look at, I should be referencing actually this number. So next we should be looking at this column. Let's look at this 4 right here. So if we integrate here from 4 to 1, square root of 4 is 2, then you'll notice in this whole region from 1 to 4, the ceiling function is going to take us up to 2. So like the square root of 4, the square root of 4 is 2 and the ceiling takes us to 2. But if you picked another number between, like if we put a 2 in here, square root of 2 is like 1.4, but the ceiling takes us to 2. So for any x value from 1 to 4, we're just going to be integrating 2 dx. Similarly, if we look at from 9 to 4, we're just going to be integrating this value here, 3 dx. Now, I won't go through all these values because it's kind of a lot, but we'll look at our last one. So when we're integrating when we're integrating from 81 to 100, everything from 81 to 100 is going to be like 9 point something, except for at 100 it's 10. But the ceiling of 9 point whatever is just going to give us 10 dx. So now this is going to give us 10 different integrals. And it turns out we can generalize this and call this number here, we'll call this n. We're integrating n dx. So you notice in each case, the upper bound is going to be n squared, and the lower bound is going to be n minus 1 squared. So we can write it like this. But what we're actually doing here, we can write as a summation. This is a series, so we can write this as the sum from n equals 1 all the way to 10. And what we can do is just integrate this thing. Now because n is just a constant, we could pull it outside the integral and just integrate 1. And so we're going to get, for integrating this, we're going to have n times x, evaluated from n squared to n minus 1 squared. Then from here, we can just evaluate this. Now, when I put a n squared in here, n squared times n is going to give us n cubed. And here, for now, let's just write this as n times n minus 1 squared. So at this point, I think you can see we're completely done with integrals and we're just dealing with the series. And we just need to simplify this thing to finish this off. So we're just going to expand this thing out. So n minus 1 squared is going to be n squared minus 2n plus 1. Then we'll just bring down our n cubed. We'll distribute in this minus n, so we're going to have minus n cubed plus 2n squared and minus n. Well, that's nice because our n cubes are going to cancel. And then I'm just going to rewrite this again. But what I'm going to do is I'm going to split this into two sums now because we have these two separate terms. So in the first one, I'm going to have n squared, but I'm going to bring my 2 out front like this. And then we'll bring a minus out front here, and we're just summing n over here. And this is going to be from n equals 1 to 10. This is nice because we've got well-known formulas for each of these. I'm going to use k just because we're already using n. So the formula for this, for the sum of the first k natural numbers, is going to be k times k minus 1 over 2. And the formula for this one's going to be k times k plus 1, 2k plus 1 all over 6 for the sum of the first k squares. And of course, our k value is going to be 10, so we just need to plug this in and calculate, and we're going to be able to finish this off. So k is going to be 10. So let's see what we have. We're going to keep our 2 out front. We're going to have 10 times 11 times, for 2 times 10 plus 1 is going to be 21 over 6. And then for this one, we're going to have 10. Sorry, that's a typo. This should be k times k plus 1. So it's going to be 10 times 11 times 2. Let's see, we can cancel a 2 and a 6 here and have a 3. I can cancel a 3 and a 21 and have a 7. Multiplying this out, 77 times 10, this is going to be 770 minus, this number is 55. That's going to give us our final solution, which is just 715. So that's it. Thought it was a good problem today. Thanks everyone for watching. Please like and subscribe. Have a good day.